the webinar, otherwise we'll continue. The panelist today is Deepak Ramasubramanian from EPRI. Then we have Xavier Guillaud, Ecole Centrale de Liège University, and then Giorgio Misyris from the Technical University of Denmark, DTU. About the multi-DC project, this project is founded by Innovation Fund Denmark, the grant solution, and this project has been running for 5 years with an edge of 3.5 million euros. The partners of this project are the two TSOs in the Nordic countries, Energinet and the Svensk Kraftnät. Besides that, we have ABB or Hitachi ABB Power Grid, who are also involved. And then we have 3 universities, KTH, University of Liège, and the NTTU. The main focus of this innovation project has been, could be said, it has been divided into 3 main areas. One is the stability of zero-inertia system. The second one is coordinated control of multi-area AC/DC system. And third, but not least, is market integration of meshed HVDC connection. Before I leave the floor to the first presenter, I would just want to inform you that we are planning to have a final event or final demonstration event of this project by the 28th of October. Please feel free to sign or register yourself. Here you have the link to register. The final event will be held at the DTU in Copenhagen, but it will be a hybrid event where the session will be broadcasted live to various channels. With that in mind, I will give the floor to the first presenter, but I would like to make a short introduction of him. And the first presenter is Mr. Deepak, who is currently a technical lead at the Electrical Power Research Institute, EPRI. His work at EPRI includes development of new and improved mathematical models and processes for large electrical systems to represent the behavior of inverter interface generation sources and loads, and evaluate and development of the transmission planning criteria, including uncertainties of source and loads. So, Mr. Deepak, you could present your presentation. I will stop sharing.
Yeah, thank you so much. Let me share my screen. Please let me know if you're able to see the presentation, and I'll transition to the slideshow mode.
Yes, we can. So you can stop.
Okay. Yeah. So thank you so much for that kind introduction, and thank you very much for inviting me to make this presentation here. I know the other folks in this panel, also Xavier and Georgios, they also will have a lot of good presenting materials on this topic of reforming inverters. So try to set the stage on what is this aspect of reforming inverters, how are we approaching it from an EPRI perspective, and what are our thoughts about how to model them and how they can be represented for future planning studies. So before we go into a lot of details from EPRI, we like to think of this as how the system needs have to evolve as you have more inverter-based resources coming into the system. Now, in the past, we had a synchronous generator-dominated system, and in that scenario, we usually would require inverter-based resources only to provide unity power factor operation, minimum fault right-through, the moment a fault occurs in the system, pretty much used to tell the inverters, you trip, we'll take care of the fault, and don't impact the system in any other way. But as we have more inverter-based resources coming into the network, we want them to have more types of services and provide more types of performance-based behavior, such as automatic voltage control, frequency response, improved ride-through behavior, and that's just going to increase. Now, even in the present day, these kind of services are in almost a slower time scale because you still have synchronous machines present in the network. But as you go towards a future IBR dominated system, we would like these inverter-based resources to provide these services in a much faster time scale. Note that we're trying to be very conscious when we talk about this, about time scale and not related to any control or any type of source behavior, because it's very important that from a system planner, we focus on time scale so that any kind of source that, as long as it can provide that service in that relevant time scale, it should be considered a valuable and a viable source for the entire system. So providing things like faster frequency response to maintain stability, voltage response, and so on. And it becomes important then as to how do we define these timescales within which these kind of services should be provided. But for few who may be new to this topic, or for those who just want to get a baseline again as to why are we talking about this so much now in the past few years in our research community and even in the industry, it makes it's good to take this perspective on why is it such a challenge for inverter-based resources to provide this kind of service. And we talk about fast timescale services. So why is it such a challenge? And in the past, when we had a synchronous generator dominated power system, the way in which this system would move around, or it would be influenced by inverter-based resource dynamics, is that any change in the power or current injection from this inverter-based resource wouldn't really move the system around. Now, here, of course, the representation of the cartoon is in terms of a mechanical movement, but you can relate that to electrical movement also. And the change in injection from these inverter-based resources wouldn't really cause an electrical movement of the system. But however, if the system itself moved its position around, then the inverter-based resource would move in tandem with the system. So in a sense, it would change its position based upon how the position of the system changed. Recently, this has been labeled as grid following. It was a characteristic that was always there since the first wind turbine integrated to the system maybe 2 decades back. But we have started labeling that as grid following in the past 5-10 years. Now, as we move towards an inverter-based resource dominated system, the elasticity of the system increases. It no longer has this kind of mechanical brakes, so to speak. It no longer has the stiffness that is associated with it because it's a pure electrical system now. And now what happens is any change in current or power injection from the inverter-based resource has the capability to move the system around. And in turn, when the system moves, the inverter-based resource will move with it. So now you have a cyclic motion which is set up wherein the inverter-based resource influences the position of the system, and the system influences the position of the inverter-based resource. This kind of a cyclic movement, if it occurs in a very fast time scale, that can become unstable. And though that is the main challenge that we want to try to tackle with inverter-based resources providing these kind of services, and we have to make that a stable response so that we have a reliable power network as we have more of these resources. In today's power network, a fast-moving system is considered an unstable system because that's how we have planned our system over the various years, that we know that the system will usually be slow-moving. So anytime the system moves fast, it is characterized as an unstable system, or it's characterized as a system which has some issues or problems associated with it. So another challenge which we will have to face as we move towards a future system is reconcile ourselves that the system will move fast. And then how do we then work with that, rather than trying to force ourselves to keep a slow moving system and keep the same characteristics as we have today. We would have to transition to a position wherein the system would be moving fast and we are fine with that movement, and how do we continue to operate the system. So this kind of fast movement, this kind of a cause and effect relationship that these inverter-based resources will share with the entire power system gives rise to this terminology of weak grids, low short circuit behavior. And we look at it from EPRI that there are multiple ways of looking at what is a weak grid. And I won't go into all the math here. I'm sure a lot of folks would already know this, but essentially we can categorize weak grid as your inductance increases or as the impedance increases, your sensitivity of voltage to current injection increases. You have a more sensitive system. That is usually characterized as a weak grid in a very high level terminology. It can also have components as in low short circuit MVA. You don't necessarily have to have a physically large impedance. You can have an apparently large impedance if you have a very low short circuit current being injected from this end of the network. So this end of the network sees a large impedance, where in reality there is no large impedance. It's just that the fault current is very low. You could also have a very high frequency transient or a rate of change of frequency. And all of these could characterize what we know as weak grids, and the characteristic of grid forming inverters could be the solution to that. This is, however, something which is not new to power systems. We have known this from synchronous machine theory for quite some time, when you had hydropower plants supplying load which was located far away through long transmission lines. And we developed concepts like power system stabilizers to help improve the stability of the network. And there's a similar thing called power oscillation dampers, which can roll into a grid forming definition because it helps improve the stability of the system. So now it comes down to how do we look at grid forming inverters, and what is a way in which we can
I think there is an internet connection problem. Deepak, are you there?
While Deepak is trying to reconnect, I think we lost him. I think maybe we should consider to use the time wisely and move on with Xavier and his presentation, and then Deepak can come back to his whenever he's capable of reconnecting. Xavier, is that fine with you?
Yes, it's okay for me.
Perfect, no problem. Perfect. Before you start sharing, I will just give a short introduction to you, or about you. Xavier, he's a professor at the Ecole Centrale of Lille, and has been professor there since 2002. His work focused on the integration of high voltage power electronics converters into the transmission system. He is involved on several projects about power electronics on the grid within the European projects, and a large number of projects with the French electrical utilities. So this is a bit who Xavier is, and thank you for joining us today.
Thank you for the introduction. I think I cannot share my screen. Can you give me a possibility?
That's a good question, how I can. Because, can you try now?
Yes, it's okay. Can you see my screen?
Yes.
Okay, so I will start my presentation about some fundamental considerations about grid forming converters, and we'll present different variants for the control and some application. So, well, we all know that there is a strong increase of the power devices in the power system for electricity generation. So I will not insist too much about this point because Deepak has already discussed about that. Well, in Europe, there are some ENSO is working on that and has published a paper which is called hyper-integration of power electronic interface power systems. You see the title on the slide, and several topics has been identified. So you see the list of the 6 topics which has been identified. So I will not go in details in all the topics, or only I will speak here about how to create system voltage and how to contribute to the inertia of the grid. So again, the idea is really to start from some fundamental basic considerations and then to analyze how is it possible to control the converter with this voltage source behavior. And from that, we will define 3 main types of grid forming controllers. So first, before starting really the presentation, I would like to say something about the modeling. Of course, it is well known that we have 2 types of power converter, well, I would say VSC, 2 types of VSC. Either we have small VSC for the PV or wind turbines. There are VSC with a classical VSC with a LC connection, or we are much larger VSC such as MMC for HVDC links. But here, in the most of the presentation, I will only use a very, very simplified VSC, which is just called, well, it's not a VSC, in fact, it is a 3-phase voltage source, which is driven by the control. Of course, I'm fully aware that this model is extremely simplified compared with the VSC. But in fact, from that, we can draw some, we can have some conclusion. And from that, we can switch to a more accurate model, and we see that we have the same kind of behavior. So the first requirement for the grid forming control, of course, is we want to have voltage behind an impedance behavior. But of course, we need to have a control of the active power. As for any kind of control for the VSC, we always have to control the active power. So let's start from the very, very basic formula that is very well known about the active power, which is active power is depending on the grid, on the variation of the angle between 2 voltage sources. So here we have 2 voltage sources, which are on one hand, the voltage which is modulated by the converter, which is called VM, and on the other hand, on the other side, we have the grid voltage, VG. So it means that if we want to control the active power, we will need to control the difference of angle between the 2 voltages. So we can, I will show you different solutions, but one of the solutions is, first we have to, when we want to control this different angle, this is the origin of the grid forming control, because all the different types of grid forming control will always try to control this different angle. In fact, there are several possibilities to control that. I will explain you how we can do that. So, well, delta, 2 angle delta are phasor angle. We can switch to time domain angle. And there is of course, with a well-known relation between the phasor and the EMT angle. So in steady state, all the frequencies are the same. So if we maintain a given value for the difference of angle in the phasor, the difference between the phasor angle, then we will have the same difference of angle between the EMT angle. So we can have, well, here we switch to EMT, and we can have the first basic control, which is where we recall the, sorry, the model of the system between the active power and the difference of angle. And for the controller, we just have integrator. It means that here we need to estimate the grid angle, and then if we have just a simple integrator, we will control the active power. This is the first possible scheme for controlling the active power, the voltage source. So if we integrate that in the control, we suppose that the control generating a reference for the voltage here, a three-phase reference for the voltage. Then we start just from VMD given magnitude for the voltage, VMQ equal to 0. Then we use inverse part transformation, and we are using the angle which has been generated by the control to generate the three-phase voltage reference. And after, of course, the low-level control will do its job to drive a correct, to drive the converter in order to have the good value for the voltage on the modulated voltage. Here we see that the system behaves as a voltage source behind an impedance. It's possible to modify this impedance. If we integrate a virtual impedance, then we are going to measure the current and then integrate, modify slightly the voltage, VMD and VMQ, in order to take into account the current and to modify the current. So in fact, it's not really a real inductance. There is no derivative, you see, in this equation, just a static impedance, but it can also be quite useful to get. It depends on, in fact, the grid impedance. Either X is sufficient or not. So if X is large enough, it's not compulsory, of course, to use this virtual impedance. So, in fact, here, and well, if we are doing this kind of control, it's very, as you see, it's very simple, and we can just show you some few results. Very simple. The result, we apply a step on P star, and then we have this answer with P around 100 milliseconds for the response time. So here, this is the first way to control the active power with a voltage source. However, we can add a third requirement for the control, is to add an inertial effect. Well, inertial effect is very well known. We know that for the inertial effect, we have a relationship between the variation of the power variation and the frequency derivative, or the double frequency derivative for the angle. So it's possible to mimic this inertial effect thanks to the control. Then we will have, it means that we need a double integrator in the control. If we add this second integrator in the control, we don't need to add any grid angle compensation, because the controller is enough to mitigate this disturbance. The grid angle here is considered as a disturbance, as you can see on this block diagram. With a double integrator, it's not needed anymore. So it's a second way to implement a grid forming control with a double integrator, and we don't need any PLL. But as you can see here, we have a double integrator again and a closed loop system. This is a very nice oscillator. Of course, it's not possible to use this kind of a system with a null damping. Then we have to add a damping effect. Of course, we will not be as close as previously to the inertial effect. We need to damp the system, and we can choose the coefficient KB as we want, since it is a control system. Then it is a second order system, so it's very, very easy to design the coefficient KP. But in fact, well, since we have only one parameter, we cannot control the response time and the damping in the same time with only one parameter. So we will choose to control the damping, and then, of course, the response time is a consequence. So as you can, we can have, we've done several studies here to see that, well, if we modify the H, the coefficient H, then we can have something like 0.7 damping. It's okay, but the response time is not controlled. Well, even if we, for several value of H, it's possible to have a, I would say, good enough response time, around 200 to 250 milliseconds. So here, as you have seen, till now, there is no current limitation, no current control. So of course, if we have a voltage source, but we have also to limit the current, we have to add a current limitation. So in normal operation, we don't need any current loop, anything. But if there is an event on the grid, then we will need to implement to activate the current limitation. So current limitation well, twofold. There is two solutions. Either we can increase the virtual impedance that I already presented to you previously, or we can use a current limitation, a current loop in the control to limit the current. I will not go into too many details about that because of time, but two solutions can be combined also to have good current control. Another, I would say, the third type of control that can be implemented for the grid forming is to add the current loop. So we still want to have a voltage source, but it's possible to add this current loop even in normal operation, not only in current limitation mode, but also. So in fact, the question is how to define the current reference. So we will use this static model of the virtual impedance also, but in the reverse way. You see here that we are previously we were generating a reference of voltage from the current measurement. Here is the contrary. We are generating a current reference from the voltage. So we are always have this value for the for the VD, and also we are measuring the voltage, and from that we have this current limitation. This current. If we have a very fast current loop, then we can suppose that the system behaves as a voltage source behind an impedance. So here we have done that on a very simple system. If we add the LC filter, as you can see, we have done the simulation to show that it works as with the ideal voltage source, and we have done also the same work on the MMC to show that we can have very good behavior for the MMC with the control that I showed you previously. So to conclude here, it's possible to control active power with a reasonable and controllable dynamics with the voltage source behind an impedance. Since the principle of the power current is based on the phasor model, active power will be slower than the current classic loop. It's possible to control the active power thanks to voltage without PLL, but it doesn't mean that voltage grid forming control doesn't need a PLL, since we have proposed, we have shown you control with the PLL. From the control which has been presented, it's possible to have an inertial effect with no frequency measurement. And this inertial effect can be parameterized. Of course, it's very different from the synchronous machine, but it's not always needed to have inertial effects. And it can be shown that there is a very robust in case it is very robust in case of EPRI. I didn't see. So there are some drawbacks. There are not always some positive effects. It's extremely sensitive to the grid event. So there is a very strong connection between the AC and the DC side. So which can be quite a bad thing for the device which are connected to the DC bus. So just to end, well, there are many pending questions about grid forming, the question of current limitation in case of unbalanced short circuit, the question of voltage pass-through capability, which has still to be studied, and the question of behavior during a fault, since it doesn't behave as a grid following control. And from the DC bus point of view, as I already mentioned, I didn't speak too much about that, but there is a really very strong connection between the wind excitation, for wind turbine with the grid forming control, and for the HVDC, there is a problem for the station which is controlling the DC bus voltage, because it cannot have in the same time a grid forming control with the inertial effect and a DC bus control. Here is the end of my presentation. More than 15 minutes. Sorry, we don't hear you.
Fitim, I think you are muted if you try to speak.
Can you hear me now?
Yep.
Yes.
Perfect. Xavier, thank you very much for your presentation. Very good presentation. There has been raised some questions in Q&A, and please keep asking all the questions that you may have. We are very glad to receive any question you have. I will just take a few of them before we move on with Deepak and your presentation, Deepak. But Xavier, the first question we have received is, why do you need to use virtual impedance?
Well, I have mentioned virtual impedance, but as I said, in fact, it's not compulsory at all. Well, I would say that it's mainly used when the connection impedance is very, very small. For example, mainly, I would say in microgrid application. In fact, for higher voltage application, for example, if you are in transmission system, the transformer is, the leakage impedance of the transformer is around 0.15 per unit. So we have done all our studies without adding any virtual impedance. I was just mentioning the virtual impedance, but in normal operation, it's not compulsory at all. It can be used to limit the current in case of short circuit.
Thank you very much. Then I have a question from myself here that I would like to ask now before we move on with Deepak. In a very weak network, does the PLL-based grid form machine experience the same instabilities with the grid falling converters?
Mm-hmm. So the question of PLLs is complex, of course, because PLL is non-linear. So it's, well, in fact, the big difference between using a PLL with a grid forming and a PLL with a grid following is that here we don't have any current loop in normal operation. So there is no interaction between the PLL and the current loop. So in fact, the system is much simpler. So, well, of course, I have presented a very brief summary of what we have done, but what we have seen, what we have noticed is that there is no real interaction here. And we are very, very robust in case of, even if we can of grid. So it's very different, again, from the grid following control here, due to this lack of current loop. Well, we have not done all the studies with the last version, the last control that I presented to you, to see if we have this interaction also. But with the two first control, we don't have. There is no real interaction with the current. By the first control, we have a PLL. The second control, there is a. Well, I didn't use a PLL, but so of course there is no interaction. But we can have the classical VSM is also used in PLL for an estimate to estimate the frequency. But again, haven't seen lots of interaction about that.
Thank you very much, Professor. Thank you very much for your presentation once more. I think we will move on with Deepak now, and then we can take the rest of the question during the panel session. Deepak, can you see if you can reconnect?
Hey, I'm here. Can you hear me?
Yes.
Yeah. Could I request, I think my internet connection became very spotty. If you could share the screen with my presentation, or Georgios, if you can, I can tell when to shift to the next slide and I can talk through that. Would be convenient?
Yeah, I can do that. Just give me a second to download it.
Yeah, no worries, Georgios. Murphy's law acts when you least expect it to act.
That's life.
COVID. Yeah.
While Georgio is trying to share, once again, please ask any question that you may have during these presentations. We will try to answer as many as them.
So can you see my screen?
Yes.
It's coming up on my end. So let's do this, Georgios. So you can directly move to slide number 5. And I can restart my presentation from there.
Okay. I'm at slide 5. Can you see my screen?
Yeah. Thanks. So as we were talking about this inverter-based control here, it makes a little bit sense to just look at it from how the present-day inverter-based controls, and I'm sure Xavier would have touched upon this, on what exactly is the mechanism and how they really operate in terms of being able to provide current injection network. So if you see on the left, what happens is there are two aspects of inverter-based resource operation. One is decided by the controller as to how the references are generated to meet a certain value of P and Q reference. And the other side is the current which is drawn out by network. Even in conventional grid, in Kirchhoff's law still plays a very crucial role, and the current drawn out by the network will be as much as what it needs in terms of
Deepak, again, we cannot hear you.
and it's the inverter-based resources current control loop behaves is what determines this kind of response achieved or obtained. The resource wants to do is it wants to try to maintain a level of current injection into the system for a level of power reference that it wants to inject. And when there is a disturbance on the network, if the voltage set point or if the voltage magnitude on the network changes, then it has to readjust its internal voltage very fast in order to provide a certain amount of response to the system. Now, these fast control loops
Deepak, can you hear me?
Yes.
We can't hear you at all. The audio is very bad.
Can you hear me now?
Yeah, barely. It is hacking quite a lot.
Oh, okay. How about now? Is it
Now
better? Is it any better?
It sounds much better.
Okay, thank you. Okay, let me try to salvage what I can of this presentation. Just move to the next slide.
Deepak, can you try to reconnect once more, because this doesn't work?
Yeah, I'm so sorry about this.
We can't hear it all.
You can't hear at all?
It is lagging quite a lot. So sometimes your Totally silent.
Yeah. How about now?
Let's give it a try more, and if it doesn't work, then I think we can continue with the Giorgio, and then you can try to reconnect.
Yeah, I can definitely do that. Is it a little bit better now to hear me?
Yes.
Yeah.
Yes, definitely.
Okay, so let's try this. The one thing I noticed before I go ahead is Spirosaur thing. Is it possible to send a Zoom number which I can call from the US? Because I only saw that there were Zoom numbers from Europe to call in. So let me know if that's possible. Then I can call in through my phone. Otherwise, I'll have to use internet or audio only. But let me try to keep presenting and see how it goes. So there are two possible ways in which we can reimagine this form of control that we want to achieve for inverter-based resources. One, on the left-hand side, is slowly varying the injected voltage or the developed voltage of the inverter-based resource as it wants to inject current into the system, and only control the current when the current hits its limit. So you're not going to actively control current. You're going to let the current be a free variable and move around so that whenever the network voltage changes, the current drawn out by the inverter is whatever the inverter or whatever the network needs. And the inverter control is not going to do anything to try to actively control that current. And only once the current hits its limit, you start controlling that current at the limit. And that's very similar or along the lines of a lot of the methods that Xavier also spoke about. The other way of doing this control or reimagining the way we would like to have controls in an inverter-based system is looking at it from the perspective that you can instead vary P reference and Q reference as is shown on the back end, and vary that as a function of both the terminal voltage and the terminal voltage magnitude and the terminal voltage angle. In this way, as the grid is changing, you are moving the inverter along with the grid in order to inject the type of current you want or the grid wants from the inverter. And that can also bring about a stable system. That, however, involves continuously controlling the current that is being injected. Now, there are pros and cons of both approaches. It's still a lot of research is needed to be done as to which would be the optimal approach. Is there an optimal approach? And what forms of different methods may be required. But what this shows is that there are many different ways in which one can have controls working in order to achieve the same objective, which at the end of the day is what the system planner wants. The system planner wants a set of services. And there are so many different ways in which we can bring about those services by different types of control architectures, which is then important because that leads to innovation, that leads to improved efficiency and improved control development. And all of this can help contribute or help increase the system strength in terms of few of the topics that we spoke about earlier, wherein there's either low short circuit MVA or high sensitivity of voltage to current injection or high rate of change of frequency. All of these can help achieve that. Now, moving to the next slide, in terms of all of, when we just take this control concept a little bit further, a lot of folks in the audience may have heard some of these buzzwords, may have heard some of these terminology being either in research articles, in other presentations around the world, and in different conferences. They might have heard things like this, right? That grid following IBR is a current source. A network with only current sources cannot be stable, and hence we need to go towards grid forming. Or things like behaves as a voltage source and not a current source. It does not have a phase lock loop. It's a virtual synchronous machine-based system, virtual oscillator control. You might have heard a lot of these points sprinkled around and mentioned in different forums or platforms and things like that. But what we see it from EPRI's perspective is that a lot of this is a control-specific definition of grid forming or a control-based definition of grid forming, which depends upon how the equipment is actually developed, and it's not really targeting what a system planner will want or what a system planner can use to define specific requirements. And to actually help further this point, if we move to the next slide, we will see that when you go to 100% current source network, Kirchhoff's law doesn't really vanish. Kirchhoff's law still exists in 100% current source network. The voltage levels are decided by the current injected and the impedance. That's definitely true. And it's definitely true that if you do not change the way you inject your current, the network can collapse. However, if you have the appropriate value of current to be injected, there is a viable solution. This is circuit theory 101. You can derive a viable solution from a network that has only current sources. So it's if we utilize this concept, then what is it so crucial about this current source, voltage source, or phase lock loop, and so on, that makes us look at all these definitions of grid forming? So moving to the next slide, we then take this concept a little bit more further, wherein we look at can this current source network be made to operate continuously? We are differentiating between black start operation here and continued system operation. Black start operation is something which we want to hopefully avoid, because that's an operating state that we don't want to keep going towards. But what we also want to look at is, supposing you have a system that has many inverter-based resources, and let's say the last synchronous machine trips, or you have an energy island created during the runtime operation of the system, can that system continue to operate in a stable manner? Can it really transition from being grid connected to grid isolated? Can it really tolerate that last synchronous machine trip? In such a scenario, it is actually possible to have a current source network to continuously operate if we change the ways in which we inject ID and IQ appropriately. So in that sense, a grid forming inverter also has to be grid following in some sense, wherein in a forward path, it can be grid forming, and in the feedback path, it can be grid following, because it needs to look at what's happening on the system, and it needs to change and adapt its position in relation to what else is happening on the network, which means it needs to follow what's happening on the network. But at the same time, it needs to be able to provide a set of references or a set of current injections that the system needs or can tolerate. So in that way, if you boil it down, what's really happening is you need to change the way in which these currents are being injected in a fast manner, which means you need fast voltage control and fast frequency control. And you can still get it with few delays in the network, because here voltage control takes precedence over frequency control. That's because a lot of our load in the system is voltage dependent or has voltage dependent characteristics. Because of that, we can give priority or preference to voltage control, which is easier to do, and frequency control can lag behind a little bit, but as long as it doesn't lag behind too much, you can actually get this current source system to continuously operate. And an example of that is now shown in the next slide, wherein we show that if you have a system wherein you put a load increase in this current source network behavior, you increase the load with 10% constant power load, but the remaining load is still, let's say, constant current or constant impedance characteristic, then with that, you can actually still bring about a very stable operation and a very fast operation. If you see the frequency plots, if you see the voltage plots as shown here, you can actually bring about a very good operation of the system when you have this kind of control implemented from a services and a performance point of view. And this is something that's reflected even if we now compare different types of grid forming control topologies which have been proposed or which have been worked on in a lot of literature. So if we move to the next slide, we see that if you compare things like virtual oscillator, Droop-based, PLL-based, virtual synchronous machine-based, matching control-based, those are all the types of control which are compared in this system. I have purposely not highlighted which figure or which color graph refers to which control, because the aim is not to compare the control across each other in terms of transient performance, because they're not optimally tuned for the system. It's just a baseline set of parameters that have been used. But you see that if I am a system planner and I am looking at these traces, they look very similar to me in terms of all the kinds of performance-based services that these different kinds of grid forming controls can provide, which means that there is an underlying similarity now when you look at a PLL-based control, a Droop-based virtual oscillator, virtual synchronous machine, and matching control. You see that there is this underlying similarity, not just to tolerate a grid islanding event which occurs at 10 seconds, but also to tolerate a subsequent three-phase fault that occurs at 15 seconds, which is shown on the right side figure. And what that results in is it results in this fact that if you are a system planner and you want to start asking for grid forming services, which we feel from our research, the sooner you do that, the better it is in the longer term, you can start doing it from the perspective of asking for fast voltage control. And if you bring that about, you can get in a lot of benefit as you go towards the longer term system response. And this is not just an EMT domain. If you move to the next slide, there is also, we have been working on showing that you can extend this to RMS domain or positive sequence domain modeling also, wherein if you use software like Power Factory in the RMS operation mode or PSSE or PSLF, you can actually simulate 100% networks now in positive sequence domain or RMS domain and get very good match with the EMT domain, because we make use of this fact that there is this underlying similarity in a lot of these controls, which means that a lot of models that exist in the software today now have the capability to do this. So here there's a comparison between looking at a load increase and decrease in EMT domain versus PSSE and seeing how well they match with each other. So this is in a way PSCAD versus PSSE results, showing that PSSE can also now show 100% positive, 100% inverter-based resource operation. And system planners can now start using this to further develop their plans for a system, develop what they want as services from inverter-based resources in these networks. They don't have to rely on a high computational burden kind of a simulation for every case studies. Mind you, we're not saying here that high computational burden studies are not required. What we're saying is bring about these additional tools in the toolkit so that now you can use a varying level of studies to understand how to plan the system and start doing it from today. You don't have to wait for simulation tool capability to improve. You don't have to wait for a future where you can run very fast simulations in high detail. You use engineering judgment and you say that, okay, these models provide this trajectory and the trend of response that is to be expected. Parameterize the model properly. That is very important. You can't expect to take an off-the-shelf model with default parameters and expect it to work. Parameterization is extremely key. But if you do that, you can start getting a lot of these responses comparing well across different simulation domains and can then use it to understand how the system behaves. So that leads me to some of my last slides, wherein if we move to the next slide, we see that what we think from EPRI side can help define a future inverter is something that is performance-based, services-based, provides this perspective of being able to operate with or without synchronous machines, operate in a cooperative manner with other inverters, provides positive contribution to load and generation balancing, positive contribution to voltage control, good fault right through, and power quality and stability, while doing all of this to meet our acceptable metrics that we have today, which is associated with reliability and security, and within equipment limits. We can't expect an inverter to provide 6 per unit fault current if it is not designed to provide 6 per unit fault current. Now, at the same time, one might say that the acceptable metrics that we have today need not necessarily be good for a future system. That is where we will have to work towards identifying what are acceptable metrics for the system of tomorrow, and then work with that to provide this inverter behavior. Note that we have intentionally said can provide optional black start capability at the bottom, because we don't expect every grid forming inverter to provide black start capability, just like how we don't expect every synchronous machine plant to be black start capable. Only certain specific synchronous machine plants are identified to be black start capable units. And that's how we envision that in the future, only few certain inverter-based resources can be identified to be black start capable. There are some examples of grid forming installations already there in the world, as shown in the next slide. Few of them are in small islands. Few of them are like a wind farm, which has been being tested, or pilot project for black start capability. There are a few battery installations in Australia. Julia gave a very good presentation in June this year, speaking about a lot of the grid forming inverter applications. There's a link at the bottom of the slide, so feel free to take a look at that. So then I'll just close out my presentation with the next slide, which just brings all of this into a closed loop, that it's important to be able to define performance-based or services-based definitions for grid forming inverters from a system planning perspective, we have to take a decision as to whether we want every grid forming resource to provide black start capability or not. If we do, that can mean a longer lead time before they come into the system. If not, we can actually start getting grid forming inverters faster into the system because once we remove black start capability, it all comes down to system stabilizing control, which there's a lot of research being done in that space. And we want to have to differentiate between system restoration versus continued system operation, because there are two different operating paradigms here, which one may be something which we never want to go into. There is a similarity that exists between so many different types of grid forming behavior and flavors. What that means is it can be easier to define performance-based specifications, and it's now left to the individual inverter manufacturer as to how they want to provide that, how they want to control their equipment in order to deliver that service. And we shouldn't be imposing a type of control architecture on them in order to deliver this kind of service. And because there is this similarity, there is also very high potential for generic models, which can be now used across multiple different simulation domains in order to study a future system. And it can help planners define what kind of performance they want for their future power network and identify what are the corners or what are the constrained cases that they may want to avoid. With that, I'll close out my presentation for today.
Fitim, we cannot hear you.
Can you hear me?
Deepak, we can hear you. I cannot hear Fitim.
Yeah.
Can you hear me now?
Yes.
Oh, sorry. Deepak, thank you very much for your very good presentation. There are some questions both in the Q&A, but also from my side, but I think I will wait with those to give Georgios a fair chance of his presentation. So I think, Giorgio, while you're preparing your presentation, I will give you a short introduction of who Giorgio is. Giorgio is currently working as a research engineer at the EPRI. His main focus areas are power system modeling, control of AC and HVDC grids, and stability analysis of power system with high penetration renewable sources. Giorgio is also a key member of this multi-DC project where he has been working since the beginning of it.
Thank you. Try to go like within 15 minutes to my presentation or a bit less. So the title of my presentation. Can you see my screen? Can you see my screen?
Yes.
My presentation. Okay. So the title of my presentation is North Sea Wind Power Hub Operation of Zero-inertia System with multiple grid forming converters operating in parallel. And what we are trying to do is to study the impact and the effect of grid forming converters on the stability of such a system without synchronous machines. A bit of a brief introduction to the North Sea Wind Power project. It's a vision of integrating up to 36 kilowatts of wind power in the North Sea, and multiple HVDC interconnections will be transferred the wind power to Denmark, Germany, Netherlands, and possibly Norway and UK in the long term. We were talking quite a lot about having an AC offshore system with point-to-point connections or a DC multi-terminal AC system at the beginning of this project. Due to the maturity of the AC technology, in this presentation we will focus on an AC offshore system with multiple point-to-point connections. Such a system, of course, we will not have synchronous machines, so the lack of rotational inertia brings a lot of challenges, and to mitigate this problem, we need fast control actions in order to preserve the stability. The system, of course, will have two objectives. The first one is actually to collect and dispatch the generated wind power and transfer it through the HVDC interconnectors to the onshore grid. And the second one is to act as a hub and exchange power between multiple AC grids, so increase the transmission capacity between synchronous or asynchronous areas. And as I said, the focus on the presentation is an AC offshore, zero-inertia offshore system with multiple point-to-point connections connecting the island to the onshore grids. So a bit on the elements and what are the operating principles of the components of such a system. We have the wind farms. Of course, the wind farms, we chose to operate in a grid following PQ mode, which means that they don't contribute to frequency and voltage regulation. The grid forming converters operate in the offshore converters operate in a grid forming mode, which means that they set the voltage and their angle at the point of common coupling, and they have fast control actions in order to mitigate the effect of the lack of inertia in the island. And the onshore converters, they operate in a grid following mode, and their objective is to control the DC voltage of the point-to-point HVDC links, and also in this case, consider that they provide constant reactive power at the point of common coupling. So as I said at the beginning, we want to study the effect of grid forming converters on system security, and we mainly focus on the three aspects. What is how the grid forming converters affect the frequency stability of a zero inertia system? What are their effect of their controls on the DC voltage deviations of the HVDC links? And also, how can we satisfy the N-1 criterion? The main contingencies that we investigate in this, and I will focus on for this presentation, it's a converter outage or a converter trip. And for some of for the first two questions, I will focus on we will not consider converter saturation, where for the N-1 criterion, we will consider that the converters also saturate. Xavier gave a good presentation of grid forming control structures here, so I will go briefly through them. So the offshore grid forming converters, as I said, they set the voltage and the angle at the point of common coupling. And we also employ QV droops and QV and PF droop characteristics in order to share the active and reactive power between them. And low pass filters and active damping controllers also can be employed in order to improve the damping ratio of eigenfrequencies that can affect the angle and voltage dynamics. As Xavier mentioned, an inner loop is used in order to protect the converters from overcurrent incidents. So here for the frequency, and since the frequency stability and the DC voltage stability concern they are mostly related to active power imbalance. In order to study them, we study the effect of the speed of the active power control. And here on the left figure, you can see the frequency for two different time responses of the active power control. As you can see on the blue curve, you can see the frequency trajectory when we have a slow active power control action. And with the red one, where you can see when we have a faster active power control action. Of course, maximum and steady frequency deviations are small. We may have a slightly larger rock-off in case of a fast active control action, but the differences are insignificant. On the right figure, you can see the effect on the DC voltage, and here you can see that the difference between the time response of the active power controller are more significant. In particular, for a slow active power control action, we have a larger DC voltage deviations, and this is caused because we allow for the DC link capacitor to be discharged, where with a fast active power control action, we have a smaller DC voltage deviations. And here, I mean, the main outcome from this slide is actually that when we think of designing the active power control, we should always look on when we have a zero inertia offshore system. And we want to design the active power control of the grid forming converters. It's better to look the DC voltage rather than the frequency. And a faster active power control action is preferable to avoid large DC voltage deviations. Of course, we cannot go too fast because if we increase the bandwidth of the active power controller, as you can see in the left figure, the eigenvalues start moving towards the right half plane. So after a certain point, the system becomes stable. So we can understand that there is a limitation of how fast we can set the active power control action. So there is a trade-off between the DC voltage stability and the small swing stability of the system. As I said at the beginning, the previous cases concern converter outputs when the grid-forming converters, they have enough headroom and they don't lead to a saturation. However, we might have the case that due to high loading scenario of the offshore converters, if one is actually, as you can see in the right, if one trips, the excessive amount of power might be redirected to the other converters, and depending on their frequency drop values, primarily depending on the frequency drop values, and their ratio, it will determine how much each converter, how much active power each converter will absorb. And you can see for a fixed drop case, so if the frequency drops are fixed and static and they don't consider how loaded were the converters at the pre-fault state, it might be the scenario that some of the converters will be overloaded and then the system will might become unstable. And so that we took a step back and then we tried to investigate actually how we can solve this problem. As I said, that due to the converter trip, the excessive amount of power that needs to be evacuated will be redirected to the converter based on the frequency drop values, and we can have equal frequency drops. So if we have two converters that have the same, we can select equal frequency drops. So that means that they will pick the same amount of power after the disturbance. We can also have a different frequency drops, which will solve the issue because they allow for different power sharing among the converters. One interesting thing is to notice that when we have equal frequency drops for converters that are connecting to the same bus, you can see that the response is much smoother. So we don't have an overshoot and we have a better power quality. However, because every converter, after a power imbalance, the amount of active power that each converter will absorb will be the same. So it's going to be independent of how loaded was the converter at the pre-fault state. The system is able to overload incidents. With the different frequency drops, what you can see here is that we have power oscillation between the offshore converters, and the larger is the distance between the frequency drops, the larger this oscillation will become. So as long one outcome actually from this slide is that as long as the offshore converters they don't become saturated, then an equal frequency drop option will be more preferable. However, in order to solve the issue, as I said, we need different frequency drops so that we make sure that even after the converter trip, all of the remaining connected converters will operate within their operational limits at the post-fault state. So we can have this kind of optimization problem, which which will try to select a feasible set of drop gains that will be different. However, will be the distance of the values will be as small as possible and try to be as close as possible to equal drops, so that we avoid power oscillation between the converters. But of course, being different, so that we allow all of the converters at the post-fault state to operate within the operational limits. And as you can see, here I'm plotting the same event for different frequency drop values. And so what we are doing is that we are selecting the frequency drops so that the converter which has the which has higher available headroom will pick up most of the active power imbalance after the disturbance. So in this way, we avoid the saturation of the converters and the system will remain stable. So the main takeaways of the presentation is that the frequency of a zero-inertia system is well controlled, and the absence of inertia is mitigated by the fast response of the grid-forming converters. And when we design the active power control of grid-forming converters, it's better to consider the effect on the DC voltages and try to make the active power control action as fast as possible in order to allow not to allow the DC voltage to deviate a lot. Of course, we cannot set the active power control action too fast, because then we might have make the system smoothly unstable. And as far as the N-1 criterion is concerned, we want to have as close as possible to equal frequency drops in order to avoid power oscillations between the converters. However, we need different frequency drops in order to allow for different power sharing among the converters and avoid saturation and keep the system stable. Thank you. I hope I finished my, I didn't use 12 minutes.
Thank you very much.
Thanks.
It was very fast and very good, Georgios.
Thanks.
There is a question here from the Q&A that I would like you to answer before we move on to the panelist session. And the question was, just 1 second, I need to find it. What will be major challenges in terms of stability and reliability for DC hubs? Is the question.
For multi-terminal DC systems, I guess. It's something that we... Okay, it's something that we didn't investigate. I guess the time scales of all the dynamics will be way faster, and since we don't have an experience of such a system, it's going to be, it's kind of a vague, I don't want to give a vague answer because there are a lot of steps from, first of all, in terms of cost, how a DC hub, if a DC hub is more cost efficient than an AC hub. Second of all, we need to have an example of how a DC hub can behave, because the main reason why we looked into an AC system with multiple point-to-point connections is that we have a better understanding, and the system operators have a better understanding of how such a system might behave, and we can set all the system requirements based on our current knowledge. So it depends on I would say, what is the time horizon of implementing a DC hub, because it's for the next 3 years, then I would say that's a bit infeasible to have solved all the issues and have answers of how we can make a DC hub work.
Thank you very much. And I think maybe we should move on with the panel discussion now. And I will just take some questions directly from the Q&A to start with. There is a question for you, Xavier, here that says the DC voltage of wind farm or wind turbines or PVs, HVDCs is always not a constant. How to realize the DC, the grid form and control in this case?
Well, yes, it's true that there is it's a good question because, well, if we have the variable DC voltage, there is no problem to implement the grid forming control if the converter, where there is a grid forming control, is not controlling the DC bus in the same time. Otherwise, we have some opposite effect, because the grid forming, for example, if the frequency is decreasing, the grid forming control with an inertial effect will provide the power. But in the same time, the DC bus will decrease, and then the DC bus controller will try to decrease the power. So these two opposite effects will be cannot be implemented at the same time. So, well, what we have done for the wind turbine is that we have implemented the DC bus voltage control on the converter, which is connected to the machine. And then on the grid side connection, we have implemented the grid forming control. But in fact, well, there is still a big issue for the connection of a wind turbine with the grid forming control. Well, but it's not really, for me, it's not the major issue for the wind turbine is not the DC bus control. It is mostly the question of the excitation of the mechanical system with the inertial effect. But it's another question.
Thank you very much for the clear answer. Deepak, I also have a question for you. The question is from my side, why do we always design the grid form converters as synchronous machines?
Why do we, or why should we?
Why should we, or why do we?
We don't. So our position is we shouldn't necessarily design grid forming inverters as synchronous machines, because inverter-based resources, they are more flexible, they are more capable, and they can provide much more functionality. So trying to limit it by designing it to completely mimic synchronous machines is maybe, in my opinion, a little bit underusing of capability. But at the same time, why there can be an attraction to do that is because by designing it to work like synchronous machines, there is the the system operators, system planners are more used to working with a synchronous machine system. The present operation practices are very much governed by synchronous machines. So trying to get inverters, grid-forming inverters work like synchronous machines can maybe help it integrate into the system of today's architecture in a more flexible manner. But in the longer term, what may end up happening is all the advantages you get with synchronous machines, you will also get the disadvantages of synchronous machines when you make inverters work like synchronous machines. So I don't think we should be designing grid-forming inverters to completely mimic synchronous machines, because we can get much more capability out of them. But I can understand the attraction that may be there for it from a synchronous planner, from a system planner perspective, because they're used to a synchronous machine operating system.
Thank you very much. Then I have a question towards Giorgio, to your presentation. Giorgio, what are the challenges when operating a zero-inertia system? And what is the role of grid-forming converter into that system? Would you say something
I would
about
say,
that?
yeah, I would say it's concerning more the limited capabilities of converters to operate with, for a long period of time with the current larger than the nominal value. And most of the instability that we have observed, even for an overload incident, was concerning the ability of the grid-forming converter to remain synchronized after you lose one converter, when this is not the case in a conventional system, because synchronous machines can operate well above their nominal value and for a longer period of time. So the first thing that we need to tackle is, and we need to understand, is how can we avoid all these cases or scenarios where the grid-forming converters will operate above the current limits. And and as we also saw, in a zero-inertia system, the frequency stability is not the main concern. It's more about trying to, because the converters naturally they respond quite fast, so they are able to maintain the power balance. It's how we have these extreme scenarios to maintain the stability when we are operating above their nominal values. And of course, a future work that should be done is to consider how the response when we have short-circuit faults, and later on the protection the protection schemes that we will use for that. Yeah.
Thank you very much, Georgios. Then I have a general question to all of you that I would like all of you to answer a bit, and that's a more future perspectives into it. Is it too early to for integrating grid-forming converters into the grid? Are we too early on that, or how do you see? We'll start with Professor Xavier, and then each of you could come with your view on, or your take on this.
I think that there are still lots of questions to solve, because of course I have presented here a very simplified study, and there are much more to study to be sure that it is stable in every situation. The question of imbalance is not that easy to solve in case of unbalanced fault, for example. Well, there are some few publications, but not that much. But well, I really think that the most important question is the connection between the AC and the DC system. Because when you have a current of grid following control, the current is following the voltage very quickly. With a very fast current loop. In case of grid-forming control, as I presented to you, I know that there are different definitions for the grid-forming control, but if we stick to the idea of the voltage source behind an impedance, then there is no current loop. And this is the voltage which is following much slower. Then it means that if you have, for example, a phase shift on the grid, then you have a very large active power variation on the DC bus. It should be worse than the short circuits. So we have to solve this kind of problem, because it may imply a very large power variation. So on the DC bus, this is a very large solicitation, excitation also. So either for the other station of our energy DC converter link, or also for the wind turbine. So I think that is very well. To sum up, in my opinion, the connection between AC and DC system is very different with the grid forming and the grid following, and it may have a very strong impact on the device which is connected on the DC bus.
Thank you very much, Professor. Deepak, could you also come with your take on this?
Yeah, my take here is it depends upon, I mean, completely agree with Xavier upon what happens on the DC side, but we also have to look at how are we here classifying grid forming and what we want from this grid forming inverters in the future network. It goes to, if we want the whole package of services, and if we want everything, including black start, including riding through, I don't know, 90-degree phase jumps and all of that, then we are far away from getting that kind of service. But however, if we are focused on looking at maintaining small signal stability, improving hosting capacity of the network to get in more inverter-based resource power into the system, improved fault ride through, if we are looking at those kind of aspects, improved voltage control, then we are probably not too far away, because there have been actually some examples even in Australia and in Texas and so on, wherein if you change the way in which you do voltage control in the inverter plant, from plant level to inverter level, you can get a much improved performance, which in a way stabilizes that system in that local region. So in large interconnected networks where you might still have to be in, where you have this interconnection still present, there's grid forming in that local sense which exists. So I think if we are talking about grid forming wherein we want all services available all the time from the inverter-based resource, then we are probably far out from getting that. But if we are talking about a subset of the services that will be available 90% of the time, then we are probably not too far out, and we can easily get that in the next few years.
Thank you very much for your take. Georgios, would you like to add something to it?
No, I think I would agree actually with Deepak's statements. I think whatever services that need to be provided in terms of active power imbalances or voltage regulation, I think grid forming we can use right away grid formings, and in order to support the grid, it's the more services that we need to add to compensate for some service that the synchronous generators can provide, that it's a challenge, like black start capability, for example. But yeah, so I agree with Deepak on what he said. So yeah.
Thank you very much, all of you, for your take on this. I would like to find a good question from the Q&A, and when there is a lot of questions, you can't prioritize which one is the best. I will go to the top and pick the first one that is unanswered. I don't know if you answered this, Professor Xavier, but do you think a nonlinear control will provide a better performance than PI for grid forming? That was a question to your presentation.
Well, it is very difficult to answer to the question. I don't know. In fact, of course, I am aware of these nonlinear controls, such as virtual oscillator and so on. We have worked with some teams from ETH Zurich during migrate projects in the European project, which is finished now. But in fact, in these years, it was not. We couldn't say that we have really big advantages. It was much more complex. That's what we are doing, but in fact, we didn't see any advantages in this project. Maybe some improvement has been done, but really, it is very difficult to compare because the mathematics is very complex, and they are not really used in the same test cases as us. So, I never saw any fair comparison. Because of course, if you have a nice VOC and a very bad group control. Of course, it will always work better, but well, we can just improve the tuning of the, I would say, the really basic control that I presented, and we already have very nice performance. Well, so it's not a very accurate answer, just some generalities about that, but well, I think that we really can do lots of things with very simple control as I presented. And just maybe a few comments to Deepak answers. Of course, I fully agree with what he said. In fact, what I presented, it may be mostly a European way to present the credit farming control, because the TSOs in Europe really emphasize on the question of voltage sources. Well, is it the good way to go to credit farming? I don't know, but well, if we really want these voltage sources which are driven, as I presented it, well, it's quite a long way to have that. But well, we can have other way to implement different control. I agree with that, of course.
Thank you very much for your answer, Professor. Time is flying away from us, so we have 2 minutes left, and I need to respect the time. People has a lot of other arrangements, so I would like to spend the last 2 minutes to thank everybody that has attended. And first and foremost, thank you to you, dear panelists, for presenting and your take on grid forming converters and what they are capable of in the future. And once again, please, for those who think multi-DC could be of interest, join us during the final demonstration event, which will take place here the 28th of October. We are more than happy to share our view with it. And there are a lot of, investigation that has been done in many areas in the multi-DC project. And we have our homepage, multidc.com, where you can find a lot of those information, a lot of papers and publication there. So once again, thank you very much for everybody who has taken your time to attend this webinar, and thank you very much to you three for sharing your view on this very important topic.
Yeah. Hey, Fitim, quick question. If it's possible to obtain a transcript of all the Q&A, if there are questions that are unanswered, we can possibly prepare a short write-up of the answers of the Q&A questions that were unanswered, and then upload it with the recording of the slides, if that's possible.
Yeah, I think it's a very good idea.
Yes, and maybe also a comment. There is somebody who is anonymous, so we cannot answer him. So if you can just send a mail if you want to have some answers, because I cannot answer him.
Yeah, it will make life easier if everyone could stand by their name, so we could see who we should answer to.
Yes, yes.
But I don't know how the Zoom works. It's not a tool that we normally use, but I think Giorgio says that we are capable of doing it. So if you have time, I would appreciate if you could give the answer to a lot of questions that has not been answered during this webinar. But once again, thank you very much to everybody, and I wish a great day to everyone, and keep safe.
Thank you.
Yeah,
See you.
Thank you, everyone.
Bye.
Thank you, everyone. Bye.
Bye.